was telling you in the previous video that when I differentiated once, I'm going to use product rule in this, and this is a constant, so I'll just differentiate this, and then I will use my envelope theorem and I'll say that this part is 0. So I'm left up with just L, and I'll differentiate L with respect to W when I do the double differentiation, and I'll get this. And this is so clear now, that when you increase your wage, the amount of labor that you would want to employ should fall. This is very general thing. From a firm's point of view, if firm has to pay a higher wage, the amount of labor that the firm will employ should be less. So this has to be less than 0. So if this is less than 0, it's a concave function. And similarly, I want you to prove it for the other thing round. So I have proved that it is concave in W. You have to prove that it is concave in V. Okay, it's a concave function. And now so these are the properties that you should know. So now we want to talk about input substitution. So just like the elasticity of substitution that we did previously, now we want to talk about input substitution, and I want to do it in the following way. So what this says is, when I go, so this is my curve that I have, isoquant, and this is my isocost curve that I have. And this is my equilibrium that I have. And when I go from one, so suppose I go from a point like this to some other point, I know that not only the capital labor ratio changes, but also W by V changes, because the slope of this also can change. So what do I want to do is the following. So I want to find out that when the price ratio changes, so supposedly I have to pay a lower wage, and as a result the relative price that I have to pay to the labor falls. So I'll repeat myself. So what I'm saying is, suppose initially the wage that I was paying was rupees 50 per day to the labor. Now suppose I have to pay rupees 25 per day. So labor is comparatively inexpensive to me, cheaper to me now. So I should be employing more of labor now. Am I right? And at the same time, because of the slope changing, because W by V changes, the slope changes. So my curve would look something like this, right? So when wage falls, the new isocost curve looks like this, and for this new isocost curve, my new equilibrium stands somewhere here. So this is my new isoquant and this is my new equilibrium. So what I want to do now is that when this changes, I go from a point like E to a point like E dash. So if I take labor here and I take capital here, the capital labor ratio that was here and the capital labor ratio that is here are different. So the capital labor ratio also changes. So I actually want to find out what happens to how does the capital labor ratio changes when my relative price that I pay to the input changes. So how does a firm respond to capital labor ratio when there is a change in the W by V ratio holding the output constant at some level? Okay, great. And now I want to talk something about the Shepherd's lemma, and that more or less finishes my chapter. So I want to talk about the Shepherd's lemma. So Shepherd's lemma is basically a trick to obtain contingent demand functions from the cost function. So what is contingent demand function? We have already discussed it. Contingent demand function for any input is is given by partial derivative of total cost with respect to that input prices. This is Shepard's lemma. Okay, so I would repeat myself. So one way to find contingent demand function is to do the following. Form a Lagrange, write WL plus VK plus lambda and the function, then differentiate this with respect to W, differentiate Lagrange with respect to labor, differentiate Lagrange with respect to capital, equate it to 0 and solve and get the contingent demand functions. One way to do this is this. The other way to find out the contingent demand function was given by Shepard and hence known as Shepard's lemma. It tells you that just simply differentiate the total cost function with respect to V and total cost function with respect to W to get the values of contingent demand function. Now what I want you to do is, in Snyder and Nicholson there is an example 10.4 in the book. All of you should try this example because this is very important and it actually uses both of the things, and you should know how to calculate contingent demand functions. They are very, very important. Okay, so now as I've already told you about short run versus long run period, so in short run my capital is fixed at some level and I can only change labor and capital is fixed. So because capital is fixed at some level and I cannot change that, if I have to write my short run cost function, it will be WL plus VK and K fixed at some level K naught. So whatever capital that the firm has is fixed. It cannot change that capital in the short run. So I'm taking K to be some constant K naught. Whereas in the long run, my cost function will be WL plus VK. And now this is also a variable and this is also a variable. Alright? Great. So because in the short run capital is fixed, I have a very important issue with me now. So how? Let's see. So this is my ISO cost line. That I have, and I have fixed the amount of capital at some level, which is K naught. Now because I have fixed the amount of level of capital, it is not necessary that at this amount K naught you are attaining tangency condition. So it is very much possible that at this K naught the ISO quant is like this, or at this K naught the ISO quant is like this, or at this K naught the ISO quant is actually tangent to the ISO cost line. So because K is fixed at some level and tangency condition required W by V equal to MRTS, I might not be able to find this tangency condition always in the short run period because capital is being fixed and it's not a variable. So I cannot fluctuate capital and hence I cannot fluctuate the values to find the equilibrium value. So in the short run, you may or may not be able to get an equilibrium condition, whereas in the long run I will always get this tangency condition. I can always find the tangency condition. So this tangency condition gives you certain value. So just to give you a solid example, say when I solve w by v equal to